Question 5 asks a few things related to the diagram in black. First, we are asked for the work energy theorem. This says that the net work done on an object is equal to the change in the object's kinetic energy. This equation shows the work energy theorem. We are told the crate is on a frictionless surface. It is initially at rest, so its initial velocity and its kinetic energy are 0. Then it is pulled 7 meters to point 2, and so its kinetic energy at point 2 is greater than 0. We are asked to find its kinetic energy at point 2, which we can call its final kinetic energy for the horizontal plane. Because the surface is frictionless, all the work done by the applied force becomes its kinetic energy. And since the only force doing work is the applied force, which we can call Fa, we can then take the work energy equation and rewrite it as work of the applied force is equal to delta Ek. We are told we can only use energy principles here. From the data page, we can find the kinetic energy equation. The change in kinetic energy is equal to half mass times final velocity squared minus half mass times initial velocity squared. And we can use this work equation, which tells us that only part of the force acting in the direction of the motion does work. Luckily, here, the direction of the force and the direction of the motion are in the same direction. And so we said all the work done on the object by the applied force becomes kinetic energy. Making these two expressions equal and substituting the applied force of 12 newtons and the distance traveled by the crate of 7 meters and the angle, which is 0 here as the force and motion are in the same direction, we can write this as equal to the final kinetic energy, which is what we want and are looking for, minus the initial kinetic energy, which was 0. Now cos of 0 degrees is 1, and solving we get a final kinetic energy of 84 joules. Let's adjust the final kinetic energy to final kinetic energy of 0.1 to 0.2 and write in its value of 84 joules, because we are now told that the crate begins to move down the slope with a constant frictional force of 21 newtons. We need to draw a free body diagram with all forces acting on the crate, and this is for the motion down the slope only. We can represent the crate with a dot. Gravitational force always acts and points downwards. The frictional force acts along the slope upwards at an angle of 20 degrees to the horizontal, and the normal force is perpendicular to the surface of the slope. Lastly, we must figure out if the crate will pass point 3 or not, and we must only use energy principles. One way to do this is to calculate the kinetic energy of the crate at point 3, and if it is positive, in other words, if it is greater than 0, this means the crate will still be moving. Start with the work energy theorem. And since the only forces influencing the crate's motion are gravity and friction, because remember the normal force does no work because it is perpendicular to the motion, we can then say that the net work is the sum of the two forces acting. The work done by gravity and friction change the crate's kinetic energy. Then the general equation for work is F delta x cos theta for each of the terms on the left. We must find the force of gravity parallel to the slope, which is at 20 degrees, so we can substitute mg sine 20 degrees for the force of gravity parallel to the slope, and find the final minus the initial kinetic energy. The initial kinetic energy is the final kinetic energy from the motion from point 1 to point 2. Substituting the mass of 3 kgs, the gravitational acceleration of 9.8, sine of 20 degrees, times by the distance, which is 6.8 meters, times by cos of 0, since the gravitational force parallel to the surface acts in the same direction as displacement, plus the frictional force of 21 newtons times the distance displaced times cos of 180 degrees, since friction acts in the opposite direction to which the crate moves and takes energy away. And we can substitute the initial kinetic energy at the top of the slope, which is 84 joules. Solving, we get a final kinetic energy at point 3 of 9.58 joules. Since the crate has a positive kinetic energy value at point 3 and not a value of 0, this means it is still moving at point 3. It has not stopped. So yes, it will pass point 3.